It is the to and fro motion of a body in a resistive medium. What are damped oscillations? It is a to and fro motion of a body in a resistive medium. The body makes to and fro motion about a point, that is due to the restoring force. In such motions, the amplitude of oscillations decreases with time. There is a decrease in the amplitude of oscillation over the time. As the body swings about the mean position, there is continuous decrease in the amplitude over the time. In every period of oscillation, this amplitude kept on decreasing. The body is moving in a resistive medium. The condition here is that body has to move in a resistive medium. Only when the body is moving in a resistive medium, the amplitude of the body, oscillating body, decreases. Why this is? Because the resistance of the medium offers the resistance to the movement of the body. The body is moving. If you imagine a simple pendulum that is oscillating about a fixed position, making to and fro motion, this bob or the pendulum is feeling a resistance with respect to the surrounding resistive medium. Therefore, the amplitude decreases. Why? Because the energy is slowly dissipating into the resistive medium. As the body swings, as the bob swings, in each cycle of oscillation, this bob, the material is giving energy to the, it is dissipating energy into the surrounding medium. Therefore, slowly the energy is dissipated, and finally, over a certain length of time, entire energy is lost into the resistive medium. Therefore, the amplitude becomes zero. Slowly, it reduces to zero. Finally, body settles into the rest position. Such a slowly diminishing amplitude in the oscillation is referred to as damped oscillations. What are damped oscillations? They are the decreasing amplitudes of oscillations in the medium. Okay. Look at the diagram here. A parent is swinging the swing. Child is sitting in the swing. Okay. As the time permits, as the time kept going, the oscillation of the body slowly dies out and finally settles in the rest position. This is an example for damped oscillation. Why do we study these vibrations, damped oscillations, etc. and so on? Because the study of vibrations are necessary to understand the behavior of matter under external applied forces. We know that all bodies possess mass and elasticity. To some extent, they are capable of vibrating. Basically, there are two kinds of oscillations. They are free and forced one. If a body is capable of vibrating by its own characteristic frequency, in the absence of an external force, is said to give free oscillations. It is said to be vibrating with free oscillations. So here in the free oscillations, there is no external force is applied into the system. It is because of the inherent characteristics of the body here itself makes the particle to vibrate under the action of forces that is inherently present within the system. Free oscillations that takes place in the absence of external forces, and the body vibrates with its own characteristic frequency. Okay, and here the oscillation of a simple pendulum is the best example for free oscillations. When you push the simple pendulum and make it to oscillate, and you allow the simple pendulum to oscillate freely without disturbing it undergoes free oscillations. And when you struck the tuning fork and left for some time, the oscillation that it produces is an example for free oscillations. Okay. So basically there are two kinds of oscillations. One is forced, another one is free. So what are forced oscillations? The vibrations that takes place under the influence of external forces are called the forced oscillations. So there are two oscillations. One is with the forced and other one is no forces, no external forces that acts on the body to vibrate. They are the free oscillations. The oscillations are the vibrations executed by the body under the absence of external forces. So when you leave the body to oscillate, it vibrates, oscillates with its own characteristic frequency. They are called the free oscillations. If there is an external force that makes the body to oscillate continuously, then it is called the forced vibration. So these oscillations, the free and forced, they come under the simple harmonic motions. They are nothing but the simple harmonic motions. So these simple harmonic motions can be this, classified into three different cases here: the free oscillations, the damped oscillations, and the forced oscillations. I told you basically there are two kinds: the free and forced. Now this look at the damped oscillation. Damped oscillation, they undergo simple harmonic motion with a decrease in amplitude and varying period due to external or internal damping forces. What is the difference with respect to the free oscillations? The free oscillations undergo simple harmonic motion with constant amplitude and period and no external influences. Here, if these oscillations undergo an external influence, if these oscillations undergo an internal damping forces, then their amplitude kept on decreasing it and also the period. So such oscillations are damped oscillation. It is the case under the free oscillation. Okay, damped oscillations are the cases under the free oscillation. The difference between these two is that is free oscillations where the amplitude is constant or no external influence on this vibrating particle or an oscillating particle. Here in damped oscillation, there is an external influence or the internal forces that inducing on the particle or the body to decrease in amplitude over the time. There is decrease in amplitude in the oscillations that takes place because of the external influence. Okay. Then the next case, it is the forced oscillations. I told you these forced oscillations were once again simple harmonic motions, but they are vibrating under the influence of an external periodic force. These oscillations are not taking place as by itself. These oscillations are executed. You are executing the oscillations by an external periodic force. If you go back to the picture, that one I shown you in the very first slide, where a man or the parent is pushing the swing. You imagine there is the man who is pushing the swing where the child is sitting. Okay, a child is sitting in the swing and the man is pushing. If the man is continuously pushing the swing at each oscillation, you will see that there will not be any this. I mean, this swing, it won't stops. It kept on oscillating. Why? Because the parent is pushing the swing at when it comes to the towards him. So you continuously pushing the swing at equal intervals, so that you can maintain the continuous swinging of the this swing continuously over longer length of time. As long as the man pushes at regular intervals, the swing is moving and coming back. Again, the man is pushing, it moves and come back. So that there is you can maintain a simple, continuous simple harmonic motion by continuously at periodic intervals the forces are given. By giving a periodic force externally at regular intervals, the oscillations can be continued over longer length of time. Okay, such force oscillation, such oscillations are called the forced oscillations. Okay, so look at this here. That's what I am explaining. This man is pushing the swing. It keeps going and come back. Again, the man pushes this. It goes and come back. Goes and come back like that. He is pushing the spring and the swing at regular intervals, and this swing kept on swinging without coming to a rest position. Okay, such motions are called forced oscillations. Here, if the man is once is pushed and left it makes a series of diminished amplitudes and finally settles into the equilibrium position. Such oscillations are called the damped oscillations. These are the oscillations of a body under the combined action of restoring force and the resistive forces. Here, the two forces are acting. One is restoring force, and other one is a resistive force. What is that restoring force? The restoring force is minus kx, that is acting opposite to the force due to gravity. Resistive forces are the forces that is because of the resistance of the medium. Because there is a medium outside, this particular medium resists the movement of forces. Okay, if the medium is viscous, for example, imagine you got a pendulum. At one instance, it is swing. You swing in the air, and in other case, you swing in the oil. Then, when you look at the oscillations, the one that is swinging in the air medium goes for a longer length of time. It makes a series of to and fro motions and slowly comes to its equilibrium position after a long time. But the same pendulum is swung in the highly viscous fluid, then it will come to its rest position much earlier. Why? Because the medium surrounding the body is resisting for its movement. Therefore, the oscillation dies out quickly in the resistive medium. So we can define the damped oscillations. These are the oscillations of the body under the combined action of restoring force and the resistive forces. Okay, and finally the body comes to rest after some time. And you look at the plot. The amplitude was large in the beginning and slowly decreasing and goes like that. Okay, slowly it is dying out. The amplitude of the oscillations slowly diminishes with time. Why this is diminishing? Why the amplitude is diminishing? Because of the resistance of the medium, and here the body is giving energy to the surrounding medium. So in each oscillation, the body has given some amount of energy to the surrounding medium. Slowly, this body kept on giving energy into surrounding medium. Therefore, energy of the body slowly is diminishing, and finally, it doesn't have any energy to give. So it stops at the equilibrium position. So energy is dissipated into the resistive medium. The swinging, the oscillating body here gives energy to the surrounding medium in every cycle of oscillation. Okay, because of the resistive forces. Because the medium is not free from resistance. Therefore, it is slowly dissipating its energy. Okay, I told you that already the damped oscillations are subjected to the restoring force. What is the restoring force? That is F is equal to minus kx. The second case is the frictional force. If the medium is surrounded by some resistive medium, then whose velocity is, energy is dissipated into the medium. And here we give Fd is equal to the resistive force is equal to mu by dx. What is this mu? Mu represents the that is damping coefficient. Every medium has its own damping. I told you that if the medium is surrounded by oil, then it is more possess more resistance than the air medium, isn't it? Likewise, every medium has its own resistance towards the movement of the particle. If the when you look at the movement of the suppose if you consider a pendulum, if you when you look at the moment of the pendulum, that is the velocity also decreases because of the resistance. If the medium surrounded by the higher resistive medium, then the velocity of the uh, the body also decreases. So the resistive force Fd is proportional to the damping coefficient, the damping of the medium, and dx by dt, that is the velocity. Okay, and the third force that is due to acceleration of gravity, force is equal to mva. You know this. Therefore, the total force here is F is equal to Fr plus Fd. See here, F is equal to, here this one, F is equal to F is equal to Fr plus Fd. Okay. Total force is F, that is due to restoring, this Fr is due to restoring force, and this is resistive force. Both are negative. This is minus kx, this is minus kx, and this is minus mu by dx by dt. This is m d square x by dt square. Therefore, this is written m d square x. Here, this m d square x. This is Fr, and this is Ft. This can be arranged to these expressions. Okay. Finally, you can get this. Okay. I'll use this screen and I'll explain this further. So, what do we have? We have three forces. We have the force due to acceleration, F is equal to ma. That is d square x by dt into m. This is one. And the second one is F is equal to minus kx. This is resistive, restoring force. Third one is Ft, we call this, it is resistive force or damping force. That is mu is equal to dx by dt. So we have here the pendulum. So it is swinging, going like this, and this is extreme end. So this is the direction of Fr. This is surrounded by some medium, surrounded by a medium. Okay, it can be air, or some other fluid, oil, etc. Okay. So this has a damping. So this has some damping value for damping. It's a change of medium, no? Change of density or change of density. This is given by mu. So this mu is different for different medium. Different for different medium. Different medium. Okay. So now, because of the higher the value for mu, lesser the velocity in the body. Okay. Therefore, this is proportional to dx by dt. The proportionality constant is, say this velocity is opposite here. So it is negative, and okay, therefore this is minus mu dx by dt. We know this. So here, what is this f? Suppose if this is f, this is f. Okay. So there are three forces. That is the this force f and fr plus ft. Force due to, that is from Newton's second law, a square x by dt square plus, write this one first, mu, because minus it is in the opposite direction taking place, plus minus kx. So that is plus kx here. It can be rewritten as d square x by dt square plus mu by m dx by dt plus k by m into x equal to 0. And I'll rewriting with certain constants, that is d square x dt square plus 2d dx by dt plus omega square x is equal to 0. Here 2b is mu by m. Omega square is k by x. See here, this particular b is called the damping constant. This dB is called the damping constant. Don't confuse with the mu, that is damping coefficient. The mu is this damping coefficient. B is called the damping constant. Okay. This is this particular is the differential equation of second order. Differential equation of second order for a damping oscillation, for set of damping oscillations. Okay. Okay. That is what you have seen here. That is what I have described here. This one. So now see that this is what we got. This is the expression we got. The second order differential with a constant 2b. Right. 2b is mu by m. Omega square is this k by m. Here. This is. So the general solution of the above differential equation can be given this way. For the differential equation, what we got this expression. The differential equation what we got was oscillations is d square x dt square plus 2b dx by dt plus omega square x is equal to 0. Okay. The general solution of above differential equation is something like x is equal to some constant a e to the power of alpha into t. Okay. Let us call this expression by 2. Above this one is by 1. Okay. Let us use mathematics. Using mathematics, that is differentiating with respect to x, with respect to time t. Which one you are differentiating? We are differentiating the displacement x. This x is the displacement. Therefore, I can the first differentiation dt is equal to alpha a e to the power of alpha t. If you do it successively, it is d square x by dt square. You get one more alpha here. Therefore, alpha square a e to the power of alpha t. Okay. We call this set 3 if you want. Now, use 3 into 1. Making use of 3 into 2. I mean 1 in 1. Equation 1. How can I write this? I can write this alpha square a e alpha t plus 2b. Look at here, 2b is there in the equation 1. And what is dx by dt? It is alpha times a e to the power of alpha into t plus omega square into x. What is x? X is a e to the power of alpha t into alpha t. So this is the, we may call this a new expression. So now I'll simplify this further because a alpha t to the power is constant. So this alpha square plus this alpha square 2b alpha plus omega square is equal to 0. Okay, is equal to 0. Here, to this is RHS. To make RHS to 0, either a to the power of e alpha t is sufficient to be 0, or this one alpha, this one is 0, then it becomes 0. Either one is sufficient to get RHS 0. But here, this alpha, this cannot be 0. Why? Because if you put alpha is equal to 0, x becomes 0. Equation straight away, that is 2, becomes 0. That is not possible. Therefore, the possibility is that you can have only alpha square plus 2b alpha plus omega square should be 0. Okay. Then should be 0. The solution is not complete. We need to evaluate the roots of this expression. We'll make use of the quadratic equation to the principle of quadratic equation to solve this one. Okay. I'll use the white screen. What we had so far right now, that is alpha square plus 2b alpha plus omega square is right now should be 0. If you make use of the quadratic, this is similar to to quadratic equation. What is that quadratic equation? It is ax square plus bx plus c is equal to 0 with the roots x is equal to minus b. I use this symbol, plus or minus root of b square minus 4ac to 2a. Isn't it? So what is the values of here? So here, with respect to this expression, a is 1. Okay, this a here it is 1, and alpha is equal to x here. Remember, and b is is equal to 2b. B cross is equal to 2b, and c is equal to omega square. Therefore, two b plus or minus b square means this b cross square is 4b square here. 4 a is 1 into c is omega square and divided by 2a. 2 into 1. Therefore, alpha is equal to this. When you take out this 4 outside the square root, it becomes 2. So 2 is a common factor, and 2 in the denominator here, so it gets cancelled. We will get finally this minus b plus or minus b square minus omega square. So this one is there. It has 2 roots now. 2 roots. That is alpha 1 and alpha 2. So I can write 1 comma 2. What is alpha 1 then? Therefore, alpha 1 is minus b. You can take plus b square minus omega square and alpha 2 is equal to minus b square minus omega square, 2 roots. Therefore, I can write with respect to x, what is that x? X is what it was, some constant a to the power alpha 1 comma 2 into t. Okay. So now new x is equal to, I change this constant to some other constant, c e to the power of alpha 1 is minus b plus root of b square minus omega square into t plus d e to the power of minus b minus b square minus omega square into t. This is a new expression. Okay, where c and d are new constants, where c and d are unknown constants. We need to get the values of c and d. When you get the values of c and d, then the solution becomes the final solution. Okay, so we need to get the values of c. So what we have, the expression for displacement, a constant of c, exponent of minus b plus root of b square minus omega square into t, plus d of e to the power of minus b minus root of b square minus omega square into t. C and d are unknown constant. We need to evaluate this. How to evaluate this constant? See, I'll come to that. So we got the solution, general solution. I already told a x is equal to a e to the alpha t. Differentiating this dx by dt, and again differentiating d square x by dt square, that is a alpha square e to the alpha t. Okay. Substituting the above equation, difference with respect to differential equation, we got this expression. I already explained this. Okay, taking common factor, and this is the alpha. So this is 1 and 2. 2. Already seen that. General solution. This is what we got. Already shown. So where c and d are constants need to be evaluated. So now we will evaluate the constants. How to evaluate this constant? I'll show you. To evaluate c and d, how to do it? We know that x is equal to c e to the power of minus b minus or plus b square minus omega square into t plus d e to the power of minus b minus b square minus omega square into t. This is what we had, isn't it? This is the displacement. This expression for displacement. We know this. So now, to get this C and D, we use the boundary condition. To get C and D, use boundary conditions. What are boundary conditions now? Suppose you have a pendulum that is swinging, isn't it? And this is V0 here, velocity is 0. When it goes to experiment, velocity is 0. So this is the displacement, we call it minus x, 0, and this plus x, experiment. This is the maximum displacement. Okay. Now, to start with you that is to time is 0. Let it be at the experiment. You start from the experiment. Let it be the experiment. Okay. So you pull this. You hold here. So V is 0 certainly, and T is 0. Right now T is 0. When you leave the bar with this pendulum, it starts swinging. Okay. So now, what is the first boundary condition is, I say T is 0. Okay, at T is 0, at T is 0, X is equal to X naught. Okay. And the second boundary condition will be V is 0, that is velocity is 0, that is equal to what? Dx by dt. Isn't it? Dx by dt is 0 at T is equal to 0. We have two cases. What is that? We can see here in two things. T is 0 there at this experiment, and X is maximum. X. Let that maximum value is X naught. And at T is equal to 0, we write V is equal to 0, that is dx by dt is 0. So these are the two conditions. Using first boundary condition, using boundary condition 1, I can write X is equal to C e to the power of, see the bracket or etc. Here it is T. At the end of the bracket you got T. What is this T? It is 0. So it is 0. Similarly, D is equal to exponent of, again bracket is there, outside the bracket T. I put T equal to 0 here because put it 0. And what is this X? At T equal to 0, it is X naught. So I change to X naught. Therefore, X naught is equal to e to the power of 0 is 1. Therefore, C, and here it is D. Okay. We call by some expression 5 or so. I don't remember what was the earlier expression. So I'll call this 5. So I got X naught equal to C plus 5. C plus D is equal to 5. Okay. Using a second boundary condition, if you use second boundary condition, we will get C minus D is equal to C minus D equal to B by X naught by root of B square minus A square. This is using second boundary condition. Using first boundary condition, we got C plus D equal to X naught. And here C minus D is B by X naught by root of B square minus omega square. Don't take it as a W here, it is omega. Okay, it's frequency, angular frequency, it's not W. Okay, we'll show this. I'll show this to be shown. This, okay, we have seen that applying boundary condition, we got X naught here, 3 plus D, and if you differentiate X with respect to time T and equal to 0, this is the expression. So what is that X? We know that X is equal to C times C to the power of something, isn't it? So if you differentiate that, that is dx by dt, you will get this expression. And again, using the boundary condition 2 here, this is boundary condition. By making use of boundary condition, use boundary condition 2 here, you will get C minus D, this. Okay, you will get this C minus C, this one, you will get this. I'll show you that how this goes to be C minus D. For that, I'll show you that c minus d is p by x naught. To show c minus d is equal to p by x naught, boundary condition 2. Boundary condition 2. Use. So we have x is equal to c e to the power of minus b plus root of b square minus omega square t plus d is equal to e to the power of minus b minus t square minus omega square into t. Okay, we have this already. What I do this differentiation with respect to time. So dx by dt is velocity. This rate of change of displacement is velocity. Therefore, v is equal to dx by dt. So differentiate this with respect to time t. So it is minus b plus b square minus omega square into e to the power of minus b plus root of b square omega square into t into c, isn't it? Plus d minus b minus b square omega square t into exponent of minus b minus b square minus omega square. Okay. So now you apply condition, that is v0 at t is 0. So 0 is equal to, this term goes, it becomes minus b minus b c here plus d minus b minus b root omega square. Okay, e to the power 0 is 1. Therefore 0 is equal to minus b, I can write c plus d plus b square minus omega square is common factor. Here it is c minus d. This is equal to x naught, we already seen. Therefore minus bx naught plus root of b square minus omega square into c minus d is equal to 0. Therefore, I can write c minus d is equal to v by x, vx naught by root of b square minus omega square. Okay. That is what here. Okay. This is the expression. We have shown that c minus d is equal to p by x naught root of b square minus omega square. Okay. This is what we see, c minus d is equal to v by vx naught root of b square minus omega square. So now we have not got the values of c and d. We got c plus d and c minus d. C plus d is x equal to x naught. C minus d is here. This way. using this by adding and subtracting. If you add this c plus d is equal to x naught plus c minus d is equal to root of d by x naught root of this, you will get c. If you subtract, you will get d. So we got c and d now. So that is substituted into the expression for x. You will get the final general solution. This is the general solution. You can get it. I'll show you. Okay. So what we have c x naught is equal to c plus d is equal to x naught, c minus d is equal to b by root of b square minus omega square. So if you add this, what happens? It becomes 2c, d and d minus d gets cancelled, is equal to x naught plus, here you got x naught dx naught by root of b square minus omega square. So I'll take it as x naught as common factor. So 1 plus b by root of b square minus omega square, and it is c, 2c there, therefore I get c by 2. Okay. Similarly, you can check by subtracting, you get d, that is equal to, you can check this by yourself. 1 minus, instead of plus, it becomes minus. So b square minus omega square. We got c and d. What was our expression for x? X is equal to some c a to the power of minus b plus root of b square minus omega square t plus d a to the power of minus b minus b square minus omega square. Isn't it? So we got c from here. Substituting for c and d, for c and d, we get x is equal to x naught by 2 1 plus b root of b square minus omega square e to the power of minus b plus root of b square minus omega square into t plus x naught by 2, that is t now, 1 minus b root of b square minus omega square e to the power of minus b minus root of b square minus omega square t. Okay, you'll get this. Okay, you can further simplify. You can simplify. Take an x naught is outside. Take an outside. This is the general. This is the general. This is the expression for displacement. For displacement. For damped oscillations. So this is expression for displacement for damped oscillations. So, okay. So now if you look at this x, okay, it is a function of is varying with respect to time t. See, as time varies, the t is varying with respect to time t, and it varies with this root of b square minus omega square. So x is varying as time with respect to time, it varies with respect to root of b square by minus omega square. Sorry, x varies as root of b square minus omega square varies. Okay, the variation of x depends on the root of b square minus omega square as t varies. Therefore, we can have two or three different cases. Let's show that. See here, the nature of x depends on the square root of b square minus omega square. We have seen that x depends on this. How it varies? Depending upon that, the displacement also varies. We can have three possible cases. What is that? B square greater than omega square. B can be greater than omega square. B square can be greater than omega square. Such a case is called the overdamping case. And if it is equal, B square is equal to omega square, it is called critical damping case. If it is less than, it will be called the underdamping case. If you plot the intensity, displacement with time, the variation of the displacement you can see it here. The black one is the overdamped case. So look at this, this one. This is the variation of displacement. It is never dies out completely. Okay, slowly the variation is slowly decreasing as exponentially. And here is the critical case. The red one is critical case. It is shortest uh, time during which the particle comes to almost equilibrium near rest position. And this is under damping case. So this under damping is a longer one. This is longer. This is longer. Under damping longer, and this is shorter. Short.